Hello everybody. Thank you, Justina, for introduction, and thank you to all the people attending this talk. I would like to start with this image of my wife's cell phone, recently cracked open by the inflated battery. Lithium-ion batteries definitely advanced a lot during the last 3 decades, but there is still a lot of room for further improvement. So here's the outline of my talk. I will start with a brief description of battery internal structure and what is a solid electrolyte interface, or CI. And then we'll quickly go to detailed description of sample preparation, experimental setup, and criteria parameters for in situ imaging, with short conclusions in the end. So a typical lithium-ion battery consists of 2 electrodes, the anode and the cathode, immersed into liquid electrolyte. And lithium ions carry a positive charge between the electrodes, and electron carry negative charge through the external circuit and power our devices. The electrodes are made of powder materials deposited on metallic current collectors. And when all components of the battery are assembled together, the last step of battery production is so-called CI formation, the last step before testing. During initial several cycles, the liquid electrolyte is reduced in the anode surface, which is typically graphite. And the reduction products coat the surface of graphite particles with a layer called solid electrolyte interface. And its properties is extremely important for battery functionality because poorly formed CI results in very rapid capacity loss and battery becomes useless. CI formation often studied in situ by AFM on model sample, which is highly rendered pyrolytic graphite. It's graphite, it's flat, it's clean. You simply place it inside a standard electrochemical cell designed for flat samples and easily get nice results, as you can see on this example. The problem is that CI that we grow here is formed on a basal plane, and how relevant is it for battery grade materials? Well, we know that lithium ions do not intercalate through the basal plane. They intercalate through the H plane, and the H plane CI formation is very poorly studied. From XPS data, we know that both thickness and composition of CI on basal plane and on cross-section on H plane of HOPG is very different. It is also different on different type of carbon materials used for battery electrodes. So ideally, we should study CI formation on each type of material individually. So we managed to perform such measurements and measure CI formation on battery-grade powder materials. You can see graphite particle, hard carbon particles, also NMC used for cathodes. And of course, we made reference measurements on HOPG in order to compare with both powder materials and with literature data. I will not focus on results of experiments per se, and we'll move to instrumental aspects of this work. So the first important step is a proper sample preparation. We mixed raw powder components of the electrode in an NMP solvent in a ball mill, and then deposited them on a substrate which may be a copper foil, which is a standard current collector, or I prefer to deposit it on a polymer tape to prepare a freestanding electrode. After that, the electrode is dried overnight in an oven, and the piece of dried electrode is placed into a silicon mold. After that, it's filled with a chemically stable epoxy. Bisphenol A or bisphenol AF works just fine. The filled mold is placed into vacuum oven for vacuum infusion. It's also an important step because it allows the epoxy to fill all the pores into the electrode. And after that, sample is cured and polished from both sides and attached to the steel substrate of AFM with conductive silver glue, which allows to provide electrical connection to the electrode. And at this step, it's very important to seal the bottom perimeter of the electrode because measurements are made in a liquid environment. If a small drop of electrolyte will drop on a substrate, it will dissolve silver glue and ruin our experiment, which we don't want, of course. Similarly, we prepared a thin sample, which is HOPG. After that, the sample is placed into a microscope, into a liquid diffusion cell, which can accommodate both flat and bulky samples. After that, we placed a piece of lithium foil on top of epoxy part of the sample and connected both this foil and the sample to external potentiostat in a two-cell configuration, brought cantilever close to the surface, and formed a liquid meniscus between the sample and the cantilever holder by injecting electrolyte from one of these syringes. And here it is ready for measurements. And also you can see a schematic representation of this setup. Now, during imaging, it's very important to acquire both AFM and electrochemical data simultaneously. For example, here you can see two identical experiments of CI formation on HOPG, but there is a certain difference with much more intensive blistering on the bottom electrode. And we can see that origin of this additional blistering is this current peak, which is associated with water reduction. So the bottom electrolyte was contaminated with water, so we can see this blistering. And by observing electrochemical CV curves, we can avoid misleading interpretation of our results caused by side reactions. Now, CI is quite gentle, and especially in liquid, so we use tapping mode imaging, and in liquid, especially in electrolyte, it's in full repulsive regime, so we have to use soft cantilevers, but in liquid, tapping mode is, well, cantilever vibration is highly damped. As you can see, amplitude resonance in air, or in argon in our case, and in liquid. And from my experience with this commercial electrolyte, we should use cantilevers with spring constant in the range of 0.3 Newton per meter to 1 Newton per meter, because cantilevers with high spring constant will likely damage the growing CI, and with low spring constant will be completely damped, specifically near surface. Here are three examples of cantilevers I used. The left one worked just fine. It has sufficiently high resonance frequency and sufficiently low spring constant. And additionally, it has long and high aspect ratio tip. And when it's close to surface, it doesn't cause strong liquid squeezing and doesn't experience significant additional damping. And its amplitude during scanning is very stable in liquid. The middle one also works fine, but slightly less stable because it has a short tip and low aspect ratio also. And near surface, it causes additional liquid squeezing and experience damping. And I had to adjust scanning parameters such as driving amplitude at set point during imaging in order not to lose surface tracking. And the right cantilever didn't work at all. It was not completely damped far from surface in liquid, but when it was brought close to surface, it was completely damped because it has a short effective tip length and low spring constant. So high aspect ratio long tip is preferred for such measurements. It's also important to know that during CI formation, surface roughness may change by order of magnitude or even higher. And therefore, scanning parameters which are fine for flat surface may not be fine for when CI is formed, because in this case, you may easily lose surface tracking or damage CI and obtain misleading results. So during imaging, it's important to adjust scanning parameters. Finally, it's a good habit to observe phase channel, because on the phase image, as in this example, we can detect early signs of surface damage caused by cantilever to the interface, which are not visible on topography channel. For example, such stripes along slow scan direction indicate surface damage, which is not critical and not strong, but still it exists, and we can adjust scanning parameters to avoid even such damage. I wrap up here with short conclusions. We made an electrochemical setup with a liquid diffusion cell, which allowed us to measure both flat and bulk samples. With this setup, we can measure a wide range of powder electrode materials and also composite electrodes, both anode and cathode. During sample preparation, it's obligatory to use chemically stable epoxy in order not to cause additional side reactions. And it's also obligatory to use electrochemical control to avoid misleading interpretation due to possible side reactions. And we should use soft and high frequency cantilevers, and preferably with high aspect ratio and long tips. Finally, I want to acknowledge support from my colleagues, financial support from Russian Science Foundation, and thank you for your attention.